Okay, now, this is the beginning of net ionic equations then. So what we need to understand is an equation such as this. We're going to need some solubility rules there. So I'll leave that there. If you need more help with the solubility rules and whether things are soluble or not, you can go watch some of the other videos. Look at the reaction that I have here. We need to recognize that as a double replacement reaction. And what happens then is we have these two guys switching partners, and we end up with NaCl and LiNO3. Now what we did before, again learning in little pieces, is we checked to see whether these products would dissolve in water or not. And we said if they both ended up aqueous, that there would be no reaction. Well, here's why. If we could look at this, all right, we're saying that this is an aqueous and this is an aqueous solution to start with, meaning we have sodium nitrate dissolved in water, NaNO3, and we have lithium chloride dissolved in water, LiCl. Well, if we have sodium nitrate dissolved in water, we no longer have sodium nitrate. What we have instead are sodium ions and nitrate ions floating around in solution, in water. An aqueous solution of sodium nitrate is actually sodium ions and nitrate ions. And the reason for that is what is called a soluble salt. And a soluble salt dissociates in water. Dissociates means it breaks into its ions. Simple terms. Breaks into its ions. So if we have lithium chloride, again, it is a soluble salt. How do I know that? Well, the rules. All nitrates are soluble. All chlorides are soluble. A few exceptions, but not those. All right, so they're dissociated when we mix the two. So now over here in our beaker, the resulting reaction are these two, that plus that. We have sodium ions. We have nitrate ions. Now, every time a sodium and a nitrate come together, you could think of it as dissociating, but they're not going to bond. They're not going to form sodium nitrate solid and float to the bottom as a precipitate, as we learned. And the reason for that is sodium nitrate soluble. Lithium and chloride. Again, ions. Well, what we're trying to find out is then, well, what about if sodium comes near the chlorine? Now, sodium and lithium, they're both positives. Nitrate and chloride ions, they're both negatives. They're not going to bond. So what about Na and Cl? Well, according to the rules, all chlorides are soluble, and so, that would be aqueous as well, meaning it's going to dissolve as well. Well, it's not going to dissolve. It's not going to come together. And then lithium nitrate. Again, we would predict that as an aqueous. All nitrates are soluble, so lithium and nitrate, when they come together, they form, or they do nothing. And so it dissociates. And so what happens is you write what is called an ionic equation dissociating the soluble salts. So Na plus NO3 minus, Li plus Cl minus, that would be the reactants in the ionic form. Sodium and chloride ions, I'm running out of space there, lithium and nitrate ions. Again, this is going to break apart, that's going to break apart, and so that would be the products in their dissociated form. So then what you do is you cross out what are known as spectator ions. A spectator ion is an ion that stays the same on both sides. So we have an Na plus and plus. We have NO3 minus, NO3 minus. Li plus and plus, and Cl minus and Cl minus. So you can see all of the ions in this reaction are considered spectator ions, meaning they do not do anything in the reaction. They start in the one form and they end up in exactly the same form. All right, now how are you able to predict this? This is really the introduction to it. Well, here's how we start. The first thing that we ask ourselves are, does the substance, does it start with hydrogen ions? So does it start with an H+? Remember cation, anion? So this is, positive ion, the cation. Is the cation a hydrogen ion? If it is, then it's an acid. So if the answer to this is yes, it does start with hydrogen. You can see each of these do. Now this is an exception we'll talk about in a second. So they're then classified as an acid. Well, strong acids dissociate. So if we're going to do a net ionic reaction, every time we get a strong acid, we've got to break it apart. Weak acids do not. they stay in the molecular form. And we're going to talk more about acids, bases, and we have a little bit with pH, and we know that strong acids 100% ionize. We've talked about that already. But if we're doing net ionic equations, strong acids dissociate, weak acids do not. So then how do you tell a strong acid from a weak acid? Here's how. The definition of a strong acid is if it has 2 or more oxygens than hydrogens, we're going to classify it as strong. 2 or more oxygens than hydrogens, it's strong. If there's no oxygen, then it has to be HCl, HBr, or HI. And the nice part about that is they are right in order on the periodic table, Cl, Br, and I, right near each other. So if they have no oxygens, it has to be one of those 3. If it has oxygens, there has to be 2 or more O's than H's. So let's consider the ones that I have on the list here. HF. Oh, everything else is weak. Everything else is weak, and I'll talk about that COOH in a second. So HF doesn't have any oxygens. It's not one of those 3, so this is a weak acid. So if we were to come across this in a net ionic reaction, or a molecular to an ionic to a net ionic, this would stay in the non-dissociated form. Undissociated, whichever one you want there. But it's not going to break apart. H2SO4. 4, 2, it has 2 more O's than H's. That makes this a strong acid, meaning it is going to dissociate into its ions. And we could talk about how it loses 1 at a time, then 2, or does it lose both? We're just going to break them in half. Positive ion, negative ion, H plus, SO4 minus 2. 3 oxygens, 1 oxygen. So again, strong acid breaks into its ions. It dissociates. 3 oxygens, 2 hydrogens. So that only has 1 more. So that's a weak acid. And so, again, undissociated, non-dissociated, whatever you want to call it, it does not break apart. HCl, it doesn't have O's. It is one of those 3. That makes that a strong acid, and it does dissociate. So this part right here, that's the key to understanding when does an acid break apart and when does it not break apart. All right, so let me just get rid of all of this and talk about COOH. This right here is called a carboxyl group. And a carboxyl group defines what is called an organic acid. Now, whenever you have that, the hydrogen at the end is the ionizable one, but we consider, for our purposes, all organic acids weak, therefore they never break apart. And so whenever we come across a carboxyl group, it is written in the undissociated or non-dissociated form. All right, so then, first thing, if it starts with a hydrogen, it's an acid, is it strong or weak? If it does not start with hydrogen, the second question, does it end in OH? If it ends in OH minus, that makes it a base. Same rule apply in that strong bases will dissociate, weak bases don't. So strong bases dissociate, weak bases don't. So then, just like acids, we have to define strong. For our purposes, group 1 and 2 except beryllium. So we consider strong bases if the cation, positive ion, is in group 1 or group 2, first column or second column on the periodic table. We call it strong, except beryllium. Everything else is weak. So everything else is weak. So lithium is in the first column of the periodic table. It's an alkali metal, group 1. Group 1s are strong. So this is a strong base. Therefore, if we come across this in a molecular equation, it does ionize or dissociate in the ionic form. Silver not being in the group 1 or 2 is a weak base. Therefore, it would stay in its molecular form. Magnesium, group 2, strong base, breaks apart. And iron, not in group 1 or 2, so a weak base, and again stays in its dissociated form. Now there's some other rules that apply to this in terms of solubility of hydroxides. This is good enough for us right now for us to be able to predict the property or the net ionic equations. Now there is one exception, and that is ammonia. Ammonia is considered a weak base. Ammonia is considered a weak base. Therefore, it would not ionize. All right, so does it start with a hydrogen ion? Does it end in a hydroxide? All right, so if those two questions are no and no, the next question would be, is it ionic? Now, the way you'd identify it is, once again, by the cation, so the positive ion. Is it a metal? Is it a metal? So if it's a metal, that's going to make it an ionic substance, which by definition makes it a salt. So then we go to the solubility rules. Is it a soluble salt or is it an insoluble salt? If it is a soluble salt, like I just talked about in the beginning, it dissociates. If it is an insoluble salt, it does not. So there's PbCl2, starts with a metal. That makes it ionic, that makes it a salt. According to the solubility rules, chlorides, all chlorides are soluble, but we have except Pb, meaning it is an insoluble salt. So we would not write that in the ionized form. It would stay undissociated. Sodium nitrate, that would be a soluble salt. Why? Well, all nitrates are soluble. All group 1 salts are soluble. So sodium and nitrate ions in the ionic form from the molecular. Sulfates, all sulfates. Some exceptions, but not iron. So that makes it a soluble salt. So you get iron ions and you get sulfate ions. And then the last one, carbonates, all carbonates. There are a few exceptions. Barium is not one of them, so that's an insoluble salt, meaning barium carbonate would be written in the molecular form. It is not going to ionize. All right, so we're getting closer. It's starting to build up, though. There's a lot of stuff to remember. Does it start with hydrogen? No. Does it end with hydroxide? No. Does it have a cation as a metal as its cation? Is it a salt, a positive, ionic, positive, negative? All right, if it is not, it's going to be one of these other two. It's going to either then be a molecule or an element. Now, the elements are easy to pick out. They're on the periodic table. Now, this would be just one atom, though. Meaning those Hofbrinkel elements that we did, we technically could classify them as an element, but really they would be a molecule. So a molecule, covalent bonds, we've been talking about that again throughout the year. And both of these, or neither of them, will dissociate. So they both stay in their molecular form. Neither of them will dissociate. So C6H6, how do I identify that? Well, if I followed the first 3 steps, everything else is going to fall into one of these 2 categories. It's either going to be an element or a molecule. But the way I would identify it is, just like I have all year, they're all nonmetals. So carbon and hydrogen both being nonmetals, this is a molecule. And a molecule, again, I'm not going to write all these again, but none of them are going to break apart. 2 nonmetals, a molecule. This would be a molecular, this is benzene, so a molecular liquid. This would be a molecular gas. We have a molecular liquid. We have a molecular gas. So all of these would be molecules. Now this one, like I said, technically it's a molecule because it's 2 atoms covalently bonded, but I would accept that it is an element as well. It's a diatomic molecule, but it's the element oxygen. And then lithium, element. And then iron, once again, an element. All right, so that's the beginnings of being able to understand and predict or how to write a net ionic equation from a chemical reaction. I'm just going to do these for you. If you want to stop and try them, you can go for it. I'll give you the answers here. All right, so label the following as strong acid, weak acid, strong base, weak base, soluble salt, insoluble salt. I have molecular liquid or gas, but really a molecule is good enough for us, and then an element. All right, so zinc nitrate. Again, first thing to ask, does it start with hydrogen? No. Does it end in hydroxide? No. Does it have a metal for its positive ion? And the answer to that is, yeah, that's zinc. So that makes it a salt. So then is it soluble or insoluble? Well, nitrates are soluble, so this is a soluble salt. Soluble salt, which means it is going to ionize in a net ionic equation from the molecular. All right, so IF5. Does it start with hydrogen? No. Does it end with hydroxide? No. Does it have a metal? No. So that would make it all nonmetals, which means it is a molecule. Because our last choice is it an element? So if we were going to do a flow chart, that would be where we would end up. So this is a molecule, which means it does not ionize. Does it start with hydrogen? Yeah, it does. All right, so it does start with hydrogen. So then it is an acid, so we have to determine is it strong or weak. It only has 1 more O than H. That makes it weak, which means it does not break apart. Technically, like we just said, that's a molecule, but we would accept an element as well. Either way, it does not ionize. Has a metal for its cation. That makes it a salt. It's a carbonate. Carbonates are insoluble. Nickel is not an exception, so that is going to not be in the ionic form. Ammonia, an exception in that it's a weak base, but you could also classify it as a molecular gas, a molecule. Either way, does not ionize. An element, the element tungsten, does not ionize. And there's that COOH. Remember, that is a carboxyl group, a weak acid, and organic acids do not ionize. All right.